So, hello, my name is Jack Foy. I work for Hiya. Let's see if I can get my navigation going here. And I'm not an operations person. I'm a developer. I came into this because I wanted to be able to ship code. And I got interested in infrastructure for that reason. So I've been interested in working on these kinds of problems off and on for about a decade now. I don't have some of the domain expertise that some people are pulling in here. What I've learned, I've often learned either from a software design perspective or I've learned on the job using resources we needed to go to production. So we got interested in Kubernetes about 2 years ago, and in June of 2015, we actually went live, and we've been continuously live since then. Oh, that's not going to work. And by that November, there was a survey that was done at the first KubeCon in San Francisco, and much to our surprise, we found out we were the largest production site. So what I'd like to talk about today is why we undertook this project. And this might end up being more of an organizational talk than a technical one. There is going to be some technical content, but it might not be as meaty as some of you would like. So be forewarned, I'm not going to be offended if you're here for a technical talk and you decide this isn't for you. And I'd like to, in particular, cover some of the lessons that we learned as we went through this. So this started with a crying intern. We have a very active internship program at the time at White Pages, now at White Pages and Hiya. We pride ourselves on the people that we recruit for this, and it was really striking when somebody got so frustrated that they were trying to get their system into production and over and over hitting the various gotchas that they found through the process. How did we get there? We had made a conscious decision to move towards a DevOps model a couple of years earlier. And we defined that as developers having responsibility for their system all the way to production. And devs loved this. They really, really liked the ability to decide when to ship their own software, the fact that they could do it more or less on a team-independent basis, the fact that we didn't have to do enormous, heavyweight, integrated test cycles across the entire stack before they could ship something to production. And they even embraced being on call as a consequence of that. But they really hated the state that our tools had arrived at in order to facilitate being able to do that. So we first undertook, when this was again kicked off by an intern having an unhappy experience in autumn 2014. And so we started doing a bigger survey just to capture what we knew or what we could learn out of the organization. And the first was that we had gone from a monorepo with a monolithic release process to extensive use of Chef across the organization. But that had two consequences. First, in some places it was just wrapping the legacy monolithic system within Chef resources. So it hadn't really become easier to ship, it had just become more isolated to ship. And second, we had been using Chef as a production site there for some years prior, and we had some cookbook customizations that made changing the overall process hard to do. And in particular, I don't have my speaker notes here. There we go. And in particular, we couldn't adopt any of the more modern cookbook software development methodologies that would allow people to define an environment and hierarchically compose their release plans out of reusable components. If you're familiar with the Ruby ecosystem, Chef, which is implemented in Ruby, moved towards a very gem-like model where you could have reusable libraries that you could then use to ship components across multiple systems. And the problem was that we couldn't really use those. We were still in kind of a mono repo with respect to our Chef cookbooks because we were tied down by these customizations and we weren't able to engineer our way out of them. We also had the problem that we couldn't kill off services. We would get to the point where we couldn't ship things easily using modern technologies because we had to go back and do the tech uplift on them, but we couldn't justify the tech uplift because the systems were no longer receiving engineering love, but the business couldn't afford to shut them off. This is a common thing. I see people nodding in the audience here that this is something that other organizations have encountered too. And so the cost of that is the explosion of complexity. It becomes very hard to do things in the simple way that you're trying to get everyone onto if you can't pull the tail forward. And I can't claim that we've completely solved this problem, but at least we've been able to call attention to it. And I'll get to how we've addressed some of it a little bit later in the talk. One of the consequences of doing deploy time evaluation and configuration is that multiple environments don't integrate well. You can't test all of your variability ahead of time and understand what the consequences of introducing a change are going to be. And so we did occasionally have cases where an unintentional change was made, but more commonly, much more commonly, we had cases where a change was intentionally made without full understanding of what the consequence of that would be. And that meant that we had to be more conservative about releasing changes because we didn't know what the effects were going to be. And on top of that, there were points of articulation within the system that couldn't be that couldn't be cached, or at least not readily cached. And so if one of the upstream services that we were pulling artifacts from went down, we could stall the entire release pipeline. And this was considered to be normal. It's just the way releases worked. And so I talked about being able to make changes with confidence. Some of that boils down to ownership. If you don't have a single owner for a given component, then nobody owns it. If everybody owns it, then nobody really owns it, and nobody is willing to put in the effort to comprehend what a given change is going to mean. And we had disagreement about how we should even be apportioning out these responsibilities and where a dev's responsibility should go to, because we didn't really have a platform. We had VMs that represented our application components, but those were considered to be owned by ops, at least as far as the operating system and the security and the network and all of those components on them. But the application was not something that the operations team understood. It was something where they would say, devs need to provide us with a set of tests so that we can prove that the app is up and running. And so we had devs who wanted to be able to ship without having to involve ops. We had ops who wanted to be able to introduce system changes that they asserted were benign or were required without having to involve dev. So we had an impedance mismatch. We didn't have a well-defined API boundary that would let each of these people have a clear area of responsibility. And so again, it became hard to characterize changes before we introduced them. And so another consequence of this was that we had shared components that were shared by historical accident. In particular, the example is if you have a load balancer and you have a single instance of your separate load balancer, but that's fronting multiple services. Now each development team that has a service that is registered on that load balancer has some place where they might need to make changes as part of a normal release because they're introducing a change to the load balancing logic or any of these other reasons. But it's something that has to be coordinated across the entire organization and intersects pretty closely with how operations wants to be running that area of the network. So this just becomes, it becomes hard to characterize what an application is. So on top of all of this, we had actually done an earlier experiment with Docker. We had identified this as a promising technology. We had said containers look like they're really interesting. And we were able to deliver a service to production using it. But that served enough to be able to tell us that we didn't have all of the infrastructure there in just being able to ship an application in a container that we would actually need in order to solve these broader system integration problems. And so we looked at what was available at the time, decided there isn't really anything here, and started looking at what it would take to be able to roll that up, and we never really got good momentum on being able to carry that forward beyond that one spike because, again, it revealed the costs, how much it was going to take for us to actually be able to do this transition. So I'd actually already written this slide when Kelsey tweeted this about a week ago. But he's outlining exactly the same problem that we had identified in early 2014 around that spike. So we were commissioned at the very end of 2014 with solving this problem by the time interns came around again. So I'm going to talk a little bit about how we solved this as an organizational problem. We decided that in order to make this happen, we needed to enable dev teams to run and admin their own applications. This is something that's sometimes called app ops or app admin these days. Again, I'm seeing people nodding and laughing in the audience, so I guess people have dealt with this model. And in order to provide that, we needed a better picture of the infrastructure than we currently had. We at the time were running on fairly manually maintained VMware vSphere configuration, and we were looking at doing a move over to some kind of cloud system. And so we tasked our ops team with becoming an infrastructure development team and providing that kind of an interface for us to be able to build on. But to join the two, we needed some kind of a platform. And we said, you know, it's great to provide the level of what an EC2 or an OpenStack does, but that's the wrong set of abstractions to enable app ops. We need some kind of a platform that provides the APIs that join those two. So we looked at what the problem was going to allow us to solve, and we decided that since most of our new backend services were stateless and Scala-based, most of our new front-end services were stateless in Flask and Python, and we had existing front-end Rails apps and legacy back-end Ruby processes, all of which were essentially stateless in front of the database or in front of a database. We decided that this was a ripe target, and in particular, we would target Scala applications because that was where most of the new back-end development that was driving this was happening. How many of you have heard this motto before? Test what we ship and ship what we test. Okay? We decided again that containerization looked like the right model for us to be able to encapsulate behaviors that we could develop and test and then byte for byte move into production. And we then said, great, that means that we need to be able to define our environments in terms of how we manage these immutable objects. There's a general principle on this, which is that you want to push variability to the left, meaning that you want to be able to encapsulate your variances in your components as early in the build process as you can, and then compose those in immutable ways as you move through your development cycle. We were using a lot of Chef, and a lot of us really liked Chef, and a lot of us really did not like Chef. And we were moving away from Ruby as an organization. So there's a general principle that can come out of this, which is that if you're doing a technology change and you want to be doing a cultural change as part of this, you can join the two and say, as I move into a new cultural realm, I do that by moving onto a new platform. So that left us with the question of how do we, in fact, configure our hosts and our clusters for use? And we evaluated CoreOS and decided that this was a pretty good model for where we wanted to go. We had been in an Ubuntu shop prior to that. We are still an Ubuntu shop within many of our container development environments, but as far as the actual hosts that we are running, we decided that our new platform would be CoreOS. We did briefly evaluate new configuration management systems. We looked at Ansible, we looked at Salt in particular because of Kubernetes' use of Salt, and we didn't really adopt any of them. We instead moved towards something with more static configuration based on user data within VMs. And we knew that we needed more than Docker in order to make this succeed. We needed some kind of an environment. And there wasn't really an obvious community consensus around this at the end of 2014. Kubernetes had been announced as a project, and we were trying to get our heads around the abstractions that they were describing. At the same time, there was Mesos and Mesosphere, and we really liked some of the things that they were doing as an organization. We were really impressed by what Joyent was doing with their applications, and in particular with the Linux personality that they were able to expose under their BSD jail mode. I'm sorry, they're under their Solaris jail mode. And Fleet was available, and because we were looking strongly at CoreOS, that was one of the options that we could use. But Fleet doesn't really provide the abstractions that we wanted to be able to manage an application. It's more targeted at managing infrastructure across a fleet. And we had a strong contingent within the team that thought that we could solve this problem better than anyone else had, and we should just bite off that project. And we ended with a strongly divided team over this, and we ended up having to pull in the CTO in order to give us a command decision on it. And he just said, management-wise, this is what we're going to do. We're going to use community standards. Pick one, but use that. Don't roll our own. And this is a hard line to walk as development organizations. You know, we're employed because we have to solve business problems, and our business problems really are all different because all of our organizations are different. But we use open source because they're not all that different. So you have this line that you have to walk between being able to use standardized components and being able to track an upstream as changes come out, versus having something that more tightly fits your use of an application. I don't always know where the line is on this. I think it's it's part of the art of engineering. So then we faced some implementation decisions. We had our own data center, and that was where we were deploying OpenStack. It's much more cost-effective to run things in your own data center if you already have one. You've already sunk the capital cost, you've already sunk the operational cost of running that infrastructure. And so your cost per cycle and cost per megabyte of RAM or gigabyte of RAM is much, much lower than using somebody else's platform. On the other hand, it's much, much more convenient to use somebody else's platform, especially since they can invest in better user tooling than typically you can. I don't know if any of you have used both OpenStack and EC2, but EC2, and I can't believe I'm about to say this, is a much more polished experience. And that's really saying something about EC2. So we knew that we needed to have something that would look common between the two, but they're really very different. They have similar abstractions, but they're not the same, and they behave very differently. And the problem was that as our role in the platform team, it was our job to then provide that common platform that our developers could use, and just the only thing they would need to know is basically the different latency or cost characteristics of where they were going to be running. They wouldn't have to know the differences about how they were going to be running the applications. Oops. So we were already on CoreOS. We reached out to CoreOS. They introduced us to Tectonic. We really liked it, but we needed it to do more than AWS. And on top of that, we were getting into January, February at this point, and their release cycle was not going to be complete early enough for us to be able to meet our deadline of not having interns use the old system by the time they came around that following summer. It was 4 months off at that point, and we expected they weren't, they told us that they couldn't commit to being able to make it. It was going to be end of summer at least before we would have something that was production ready. We took a look at Fabricate. I don't know if you've seen Fabricate demos. It's an amazing piece of technology where you can deploy an application. It's very, very close to OpenShift. And you can drop in these pre-built applications and they distribute automatically into your cluster. But it was very tightly coupled. And we started picking it apart and finding places where the model, again, wasn't going to work for what we were trying to do. And it wasn't clear that we could really easily flex it to do what we did need it to do. So we took a step back away from that more integrated solution. We also took a close look at GKE. This came online pretty late in our process. We really, really liked a lot of the capabilities, and we really, really were attracted to the idea of not having to run our own cluster. But it would mean introducing a new cloud, and we already had other investments in AWS and other investments in the data center. And so we said we can't really capitalize on that right now. So then we started looking at doing our own self-management of these clusters. And naturally, we looked at using KubeUp because that's where all of the documentation points you, and you want to be able to start your own cluster and bring it up. But even if you do that, first, the result still isn't production ready. And second, it's very opinionated about how you're going to be structuring your AWS environment or your OpenStack environment. And in addition, the OpenStack integration was basically non-existent. And so we'd have to go in and invent a whole bunch of it anyway if we were going to make that happen. And on top of that, it was very CentOS-centric, and we were not a CentOS shop at all. You know, we had done we were heavily Ubuntu. We had started moving into CoreOS, and we just looked at that and said we don't really want to pull in another platform we'd have to support. They did have some CoreOS support, but it was very Rackspace specific. So we took all of that as input and produced our own set of fleet configurations. And because you're running a bunch of fleets, we called it Armada. And it took the CoreOS images and the latest Kubernetes available at the time, which was 0.17, and deployed it effectively onto OpenStack first and then AWS. And this worked pretty well for us. It allowed us to do exactly what we needed. The downside is you're maintaining it yourself, and you don't get to capitalize on the new changes that are coming down from CoreOS. And as it turns out, the CoreOS development cycle doesn't always distinguish which parts of new functionality are getting initialized via the core APIs, or at least at the time this is true, and via the cluster scripts. And so as new functionality gets introduced as kind of hacks into the cluster scripts, you have to then reverse engineer where those are coming in and make sure that your cluster maintenance stuff is keeping up with it. It's a bigger engineering challenge than it appears to be at the beginning. And again, we get into this question of customization and how much are you willing to carry forward, and how much are you willing to just drop in as upstream comes in. And it was entirely manual as far as sizing clusters and so on. We could add new capacity to clusters as we went, but it was manual. We didn't tie into any auto-scaling. We also produced our own developer dashboard, which was called Archimedes, and that worked really well. And the intent was that we were going to open source it, but we never did. And that was because it was tightly coupled to our own processes. It was tightly coupled to a bunch of our own internal interface libraries and CSS objects that we couldn't open source. And we delayed long enough that basically Kubernetes dashboard has largely caught up with where we would be if we open sourced it today. So today we're largely just running Kubernetes dashboard internally, and we have a backlog of things that we want to extend it and open source onto that. So if you're going to do this today, I would suggest just get behind Kube dashboard and push. Don't write your own. But that didn't exist at the time. There was no such thing as Kube Dash. Containers are leaky. Kubernetes, Linux containers are not perfectly namespaced. They're not perfectly isolated. There are many, many shared structures within the kernel. And so they're not really secure. It's not airtight. You know, this is one of the main arguments that Joyent makes about why you want to use an open Solaris zone approach rather than using containers that are layered into the kernel after the fact. And so we decided to isolate our directly internet-facing traffic from things that were not internet-facing and be able to at least sandbox things in that way. We eventually abandoned this. It's probably still a good idea architecturally, but the operational pain associated with maintaining these things and being able to do your work distribution across two of them, and again, we had nothing like federation, made this eventually a non-starter. You could still do something like this today if you were to do things like node selectors, if you were going to constrain your external versus internal traffic within a single cluster to nodes. I think we're almost there. I think you would need a node exclusion policy in order to keep internal traffic off of external nodes if you were going to do that. So you could get most of this effect today. For networking, the infrastructure group provided us with a tenant network. We were the first group to be using tenant networks on this OpenStack cluster or within this group's maintenance. And so we got to discover lots of the ways in which tenant networks were not fully baked. Those are implemented as a VXLAN overlay on top of a physical network. As it happened, we were also using a VXLAN overlay within the cluster for a pod network. So you end up with VXLAN over VXLAN, latency gets very high. It's a very janky kind of setup. But again, for V1, it worked. The major problems I'll get to in a minute about where we had to diagnose issues on that. We were using kube proxy, V1, sending all traffic through user space. That was really the major origin of our latency issues. But this VXLAN on VXLAN emergent property ended up making errors very hard to diagnose. Container logging. We had an existing agent that we were using for log gathering from our existing applications. We had a Flume agent that we ran throughout, and that would send log streams to a Kafka bus that we would then forward on to things like log indexers or archival services or that sort of thing. And that worked, again, pretty well. We had a UDP connection from the application to the Flume agent, and so it was inherently non-blocking. But that also meant that we were dealing with inherent size limitations like 64K max size on messages. And that gets even smaller depending on what your network stack is doing for MTU locally within your container. And so that ended up having some nasty limitations that emerged over time. But again, for the core mission, it was working pretty well. We built containers via an SBT plugin. SBT is the Scala common build tool. I don't think the Docker file plugins were available at the time, so I believe we just had something that was templating a very simple Docker file and emitting it, and then building that through Jenkins and publishing to our existing Artifactory repo, which we then licensed in order to enable the Docker image repo. So this is how we went live. We were at Kubernetes 0.17. We were on CoreOS. We used Fleet to deploy that. We were on OpenStack Icehouse, which itself was a pretty old release by that point. And we were on our own hardware. Our first customers were async Kafka workers, which were supporting some of our mobile apps, followed by some of the internet-facing helper services. We had things like name auto-completion that are firing off async HTTP requests, and so we were fielding those out of Kubernetes. We hadn't yet moved the main app over, the main Rails app over to Kubernetes, but this was a great way to start getting some operational experience with running things in production. And we had a new flagship application that we were preparing to take massive traffic on that was also one of the major first users on this. And by and large, with the exception of the networking things that I'm going to get into in a minute, our users were very happy. So this is an example of a quote that somebody came and excitedly told me about a week or two after we'd gone live, that he had hit go on a release and said, oh shit, and had to go back and scramble to fix a bug that he just realized he'd sent it, and he was able to finish the second deployment cycle fixing the bug in production before the alert for introducing the bug had hit his phone. And so that was considered just an enormous success compared to the close to an hour release cycle that users previously had to go through in order to converge application state. And the intern came back. So as some follow-ons, and I'm getting short on time here, so I'm going to breeze through a bunch of this. We upgraded to Kube 1.1 pretty quickly. We built a custom kubelet in order to improve the namespacing behavior. Some of our monitoring stuff really wanted to be able to use the host name in a distinguishable way, and that meant we had to bring pod information through into the container in such a way that a host name would answer with it. And this eventually became the default container behavior in 1.2, but we were running a custom kubelet for a while in order to get this behavior. We expanded to include auto-scaling. We never did end up using heat auto-scaling within OpenStack. It just, the heat implementation within our version just never really got there. But we expanded onto AWS and used auto-scaling there. We eventually did solve TLS, but I'll get to that a little bit later. I've talked about networking. We had very high baseline latency, which we later discovered is probably the result of running kubeproxy in user space. When we upgraded to Kube 1.1 and brought in its version of kubeproxy, we enabled IP tables, saw that it worked like a charm, and the latencies dropped way down. So if you are using kubeproxy and you're not enabling IP tables, you should really take a look. It's a massive improvement. But we still had this problem of opaque network failures, where all of a sudden we would start throwing connection errors and connection resets within interfaces on the overlay network, and typically isolated to a single node. But bouncing the node, sometimes but not always, fixed it. And we eventually discovered that was because that hypervisor configuration for a contract max, which is the maximum number of active connections that you can have across the entire hypervisor, was setting correctly on a few nodes within the cluster. So the catch on this was it wasn't our bug, but it was hard for us to demonstrate that it wasn't our bug because of the opacity of the implementation that we put on top of it. And the other lesson on this is that all abstractions leak. No matter if we're running Kubernetes or we're running VMs or whichever, at some point, eventually, the underlying layers can get you. And so you have to be able to reason past your current level. Dockerd is the bane of my existence. It turns out that the log options changed a bit across some of the major versions, and the Docker daemon didn't fail to start if it didn't recognize them. It would just ignore the option. So we'd end up with cases where log rotation would break, and we'd end up filling up disks, and we had no sign of it until the disks filled up again. External load balancers. We didn't have the OpenStack HA proxy integration in place, and so we used our traditional external load balancers, which had worked pretty well. But we discovered that there's a bug in the DNS pool discovery on that we were using in order to advertise new nodes to this pool, and suddenly the pool would empty and we'd lose production traffic. Not where you want to be. So that was all within White Pages, which was kind of the parent company where all of this happened. Earlier this year, we spun out as a startup into a new organization called Hiya. We are tasked with fixing spam and scam calls. If you get robocalls, we're trying to stop that. And we took the Kubernetes clusters with us when we went. The entire platform team wholesale got moved over to the startup. And we determined that that was a good interface for us to draw then. If we're not going to have the infrastructure team with our organization anymore, we're going to replace them with AWS. So we moved wholesale over into the cloud. And we ported our existing stuff over to CloudFormation. We use that to configure our stuff automatically now. It works pretty well, but we still have problems. We moved to using the host gateway backend for Flannel, which is marvelous. It just works. It's high performance. We've had no issues with it. With autoscaling, we took the time to do a full TLS root key ceremony, with an offline machine and everything, and a copy of the key kept off-site. And that has allowed us to take a few more risks with doing things like putting a derived key up in an automatic cert authority. And so now we have TLS handled automatically as we autoscale. We're using CFSSL to do that. It's a great component out of Cloudflare. And so if you're doing autoscaling, you should really take a look at that product. Most devs actually, once they got used to it, decided they didn't need the UI, and they just started using the config files directly. And mostly they haven't minded. We might choose to work with some higher level abstractions eventually, but for the most part, they're saying, yeah, I can just write a deployment and I'm off and running. I don't need to worry about it. We're using hosted Artifactory now, and this is great for the people who are in North America, but we also have European engineers, and they really don't like this because the latency is even worse than it was before. So we're looking at moving our image hosting directly into S3. Don't ever use CloudFormation to add an ELB to an autoscaling group. I see people laughing here. It sounds like other people have seen this too. CloudFormation will delete your autoscaling group if you do this. You lose your entire production cluster. It did not make us happy. If we move to Kubernetes 1.4, which we haven't yet, we believe that load balancer services will give us the automatic handling on this that will make us not have to do ELB management directly at all anymore. And so that will have the benefit of solving this problem and move it back into the developer's hands, which is where it should be. Container logging is still not working well. I would love to be using journald for this, but we've done some extensive profiling, and in spite of the CoreOS-driven latency solutions that they have put into place, and they've had a couple of blog posts on that, throughput is still not where it needs to be. In fact, it's surprisingly low. We're seeing things max out under 1,000 a second. So this wouldn't be a problem except that Rocket is proposing to use journal as its container logging system of record. And if you have solved any problem like this of handling high throughput container logging, I'd love to talk to you. I really want to get Docker out of the picture. This is not a universally loved opinion, but I'd rather we stop using Docker and move directly to Rocket. So this is where we are today. A year ago, we had 35 nodes in one site. Now we have about 80 nodes in 9 sites around the world. We know for sure that we are not the largest production site anymore, but I believe we're still the oldest continuously operating one. So we're pretty short on time, but I'd love to take at least a couple of questions before we go. Do we have time for that, folks in the back? Yeah, I'm getting nod, yes. Are there any questions? Yeah.
What were the features in Kubernetes that made this a success?
What were the features in Kubernetes that made this a success? Not having to have individual devs map their production use for their app directly onto the infrastructure, I think is, that's the core problem that Kubernetes is solving. And I think that really is one of the core things that let us say, you can just ship stuff into the cluster and it will find the resources for you and use them automatically. And you can then get visibility into how your app is running, but you don't have to tell it how to do that. And that's in contrast to where we were before, where we had essentially custom assigned VMs, where a user would say, I want to build front end 5, and you'd end up with a new copy of the front end VM, and the operations team would have to get involved with scheduling that. Anything else? Yeah. Do we do any security scanning on our containers or on our registry? Nothing automatic. And it's on the backlog. Right now, we basically just keep an eye out on the CVEs and keep our base images patched. But we don't yet have anything that can, for example, automatically pull out-of-date base images from use. And that's obviously desirable. Yeah? How have we been upgrading Kubernetes or any other components that would affect infrastructure downtime? We've been doing cluster replacement and load migration so far. I would love to get away from that. I think we're approaching a state where we can do that now that we're going to be able to do HA upgrades of the core components and then the kube load alongside it. But we haven't proven that out yet. So right now it's a fairly heavyweight process. We spin up a new environment, move load to it, and then spin down the old one. Anything else? All right, thank you very much.